Good morning to everybody. Today, let's talk about the software, and of course, and we have already MV opened. And today we are proceeding with the number 6, and in which today we are fundamentally introduce two different topics. The first one is mainly related to the scalar plots, in which we also use the algebraic operation. While in the second part, we will talk about digital filtering. That is a very interesting aspect of our processing, and is also very surprising in the results. Okay, let's start this lab, and I will start as usual as loading our data. Maybe today, let's open another file. Let's go to the optical sensor, open file, optical sensor Landsat here, and let's open GeoTIFF with metadata, of course, as usual. And in this case, let's go to the directory where we have the data. All right, so here it is. Let's go to the folder Southeastern USA. All right, so let's change that. This is the metadata file, you see. You see this data is acquired by Landsat 7, and you see here in the name, of course, it's very old, because it was acquired the 22nd of April 2002. So it's more than 90, is almost 19 years ago. So I mean, it's quite old. Let's double click on that, and let's open that. All right. As usual, we have the image in the visible. Let's zoom out. You see, is a scene of Landsat 7. You see here where we have a part of sea and a part of land. In order to understand where we are, we can go in view here, you see, and open the reference map link. All right, let's open it and let's see where we are. You see, you need an internet access. You see, we are in the southeast of the States, and in particular in Florida. You see here. In the central part of the Florida, where you see here we have Melbourne, and it's centered in Orlando, more or less, and Orlando, for who is following the American sports, this is the place where last year the NBA, the basketball, organized the bubble in Orlando. And you see here we are also just close to Tampa Bay, that is maybe outside of the image, that is very famous because again, for who is following the American sports, for the football, I mean the last Super Bowl was won by the Tampa Bay Buccaneers team. All right, so this is a central part of Florida, and in particular, we are in this area. Orlando should be just here in the middle, you see. And what is very important in this area, why we are here, and if we are zooming in, you see, and we are going towards the coastline, you see here is, as you know, the Florida is a very swampy country, it's very flat. And you see, when we are zooming here, you see just north of Melbourne, you see we are in Titusville, and you see here, when we are going just south, you see here we have Cape Canaveral. And Cape Canaveral is the area in which there's the missile base, a NASA base, where they are launching most vectors that are embarking on board satellites, and also, for example, many of the satellites we are using for the remote sensing were launched exactly from this base. This is a very important area for us because, I mean, it's very connected with our activities in remote sensing. All right, very good. So as usual, in order to better characterize this area that you see, I don't know if you have ever been in Florida, but it's a very and extremely flat area and very humid. You see there are a bunch of lakes and swamps in this area because it's a very wet, it's a wetland area, and there are a swamp that were restored during times. And you see that also Cape Canaveral, it's a sort of isthmus that I mean there's a channel, and these are very swampy areas. That wetlands where they have the missile base. Why the missile base is there? And for example, it's something that I'm asking to you, why the missile base in the States are mainly in the southern part of the state, because you know that most part of the missile base in the States are in Florida and in California, and so let's understand why they are there and not in other part of the States. Why not in Alaska, for example? So let's try to investigate the reason why they are there. So, but this is not part of our lab. So, I mean, maybe during one of my Thursday, we will talk about that. So, this is the image in the visible, of course, and you know that comes from the preferences, from the custom preferences we have. So, as we are doing as usual, we are going to the data manager. Let's use the band selection. And remember that here we are in Landsat 7, so we don't have any indication of the metadata of the name of the spectral bands. So, and consider that in Landsat 7, the first 3 bands are the 3 bands of the visible. So that means that the 1 is blue, 2 is green, 3 and red, 4 is the near infrared, and 5 and 7 are the mid-infrared. 6.1 and 6.2, of course, are thermal infrared, so why the band 8 is the panchromatic band. So, for example, as usual, let's open the false color image to RGB for 3 to the green and to the blue, the band 2. Let's load the data in the same view. And you see here we have the false color. Let's close that. And you see this is the display in the false color composite. Let's open a stretch, for example, a Gaussian one. You see here, for example, okay. This is an area that fundamentally is vegetated but very swampy. You see there are some urban areas. There are no very large agricultural area. You see there are much water, roads inside of these different urban areas, and this is the classical area that you can find in Florida. So very humid and very flat areas with very low variation in the texture of the image. So, all right, what we can do with this image? So, we left this topic at this time because what we want to do in this first time of the lab, in this first part of the lab, is to talk about scatter plots. So you remember that scatter plots is in the theoretical part is related to the basic processing of the image. Remember that the scatter plots is something that is not very different to a density slice, but when the density slicing has a monodimensional spectral domain, the scatter plots is the same things of the density slice, but in 2 dimensions, 2 spectral dimensions. So let's use now these scatter plots in order to understand how the data are distributed and how they can give us information about the statistical part. All right, so you remember that in the density slicing, we associate colors to ranges of digital number. So we will see in this lab that also the scatter plots can be used in this way, but of course, taking into consideration a couple of spectral bands instead of only one. All right, so you remember that last time when we talked about algebraic operation, you see that we are actually extracting this data using algebraic operation, doing something that is really similar to the density slice. So we will do the same using the scatter plots. So the scatter plots actually is the ability to visualize a two-dimensional diagram in which, of course, we can do that in n dimension, but of course, on our monitor, we can only represent something that is bidimensional. And I mean, in this diagram, we have the range of the different digital number in 2 different spectral bands. And so we are visualizing, you remember that from the theoretical parts, point clouds that are representing in coordinates, in radiometric coordinates, the position inside these this bidimensional diagram. All right, so this, of course, the data could be calibrated or not. This doesn't matter in this case. Of course, we will calibrate everything, but in this case, we can also use images that are not really calibrated. All right, let's see how we can generate the scatter plots. You see, the scatter plot is something that is working in visualizing, so it's not in the toolbox, but you see it's in the main display, and you see that you have in the main menu, that is an operation that is affecting the display. So you see here that in this pop-up menu, you have the 2D scatter plots. Let's launch that, all right? And you see that now we have these things here. You see here, this is the diagram of the diagram. All right, so I have that may be larger than you, but that's because I have enlarged that before. So in the X and the Y axis, you see we have a digital number. In this case, we have Lanza 7. We have not pre-processed. We have not calibrated the data, and so I mean the radiometric resolution of this data set is 8-bit. So we have data ranging from 0 to 255. So we are not calibrating this data in order to have something that is more easy to understand. And you see, in both the axes, you see, for example, I have in the X, I have band 4, so the near infinite in the X axis, and in the Y axis, I have band 3, for example, that is the red one, all right? This is the representation of these point clouds, you see. How many points we have in this diagram? In this case, in this particular case, the points are equal to the number of cells that we have in the display window. So, I mean, in this part, we are seeing a part of the whole image. And so here we have hundreds of thousands of different points, because every single point represents a single cell of the image with a 2 digital number in the 2 different bands. But you see that if I'm changing the zoom factor, you see that also when I'm pan, you see that the scatter plot is changing, of course, you see, because it's depending on what I'm representing, you see. My opinion is that when you are using these scatter plots, you need to use a particularly large zoom. Otherwise, if you are looking at the background of the image, I mean, this is not data, So you see, for example, when I'm moving towards the water, you see I'm moving towards the water, you see that I have, in correspondence to the water, in the band 4 and in the band 3 are highly correlated. So let's go back to the theoretical path. If I'm going, if I'm center the windows only in the water, you see that the correlation between the near infrared band and the red one is very high, because to very low value of band 4, we have a very low value on band 3, and to higher value of band 4, we have in correspondence higher value in the band 3, in the red. So pay attention to the scale, you see, because here is ranging from 0 to around 40 in the near infrared, because you know the near infrared is a very good absorber in correspondence to the water, while you see that in the red is ranging between 40 and around 90, you see. So I mean the maximum value here are in the near infrared are not more than 40. And in the red, you see, are very slightly more than 90. And so pay attention to the scale of this diagram, and you see that it's very interactive, this color plot, because when you are moving, it changes. So when I'm changing that, you see, I'm seeing something else, something different. For example, if I'm going to an area where I have only vegetation, so I'm zooming here, you see, and this is part of vegetation, you see, when I'm in the part of vegetation, this is very important, because you see that in the theoretical part, when you remember from the theoretical part that when we have correlation, the correlation is positive, so that means that it is inclined as the in that direction. While when you have these things here in this point cloud, that means that in the vegetation in this area, the correlation is particularly low, because to a particular value of the near infrared, you see from 40 to 120, we have always the same values in the red band. Why? In particular here, in that part here, we have a correlation that is positive. To higher value of band 4, we have a higher value of red band, okay? All right, so let's try to understand these scatter plots in another way. So let's open the possibility here that we have in the menu of the scatter plot. So you see help. As usual, we have all the information about the scatter plots. And in file, you see here, I can have some more information. So, for example, let's select a new band, because by default, in this case, having opened that in the near infrared, in the false color, we're using near infrared red. Now I want to change the band that I have in the band X, so I'm selecting band 3, for example, and you see, I do that by, if you have the same bands in the scatter plots, I have the same bands. Of course, I have this representation that is a straight line. This is the bisector of this diagram, because every single cell has the same value in the two different axes. So it's quite clear, these things. So I did that on purpose, of course. But if I'm selecting in the y-axis another bands, for example, the band 2, let's see that band 2 in vegetation and band 3, they are highly correlated. Very low value for the red corresponds a very low value of green, and vice versa for higher value. If I'm moving, you see, for example, in the middle of the water, you see that also here the correlation is very high. I mean, it's high enough in order to consider the two bands extremely correlated. So if I'm zooming here, zooming out, you see that considering two different surfaces, for example, water and vegetation, you see that also in this case, when we have two very different surfaces, you see that the green and the red bands are very correlated. So you see, also if I'm zooming out, you see, apart from the backgrounds, but you see when I'm center in the image, you see that I mean the correlation is still very high. Let's see if this correlation is true also for band 3 red and band 1, that is the blue band. So select on the y-axis, for example, the band 1, the band blue, the blue band, and we see if that is more or less similar. Yes, you see here that is quite similar. I remind you that these bands is not corrected by the selective scattering, but you see that there's also in this case a very high correlation. Is there also a correlation between, if I'm changing the X bands, the band 2? So we are looking if there's correlation between green and blue. So you see that they are very correlated. So that means that if, for example, now if I'm putting that in the y-axis, the band 4, you see here, they are not correlated enough at all. So you see that, when I'm trying to correlate near infrared and one of the band of the visible, you see that the correlation is not so high. So it's the same for the near infrared and red, for example, as the beginning. All right, let's see what correlation exists between an infrared, near infrared band and a mid infrared band. So in the x-axis, we are substituting with the band 5. So now you see we have band 4 in the y and band 5 in the x. There's a sort of correlation, but it's not very high, you see, because it's very dispersed, the point clouds on the scatter plots. So you see that there are part of these point clouds that are not really correlated. So let's see that these very large point clouds are representing different behavior that, for example, are representing different surfaces. For example, one surface that is very correlated along that direction, and another surface that is correlated along that direction. You see the mouse that is moving here. So that could be caused by the different surfaces that we have in the visualization. So, for example, these point clouds could be representative of two different correlations, you see? For example, here we have vegetation of the land and we have the part of water in the same views. So, let's see in the last time if the band 5 is correlated with band 7, two mid-infrared bands. So, let's substitute band 4 in the y-axis and let's put the band 7, you see that the mid-infrared bands are very correlated. You see here to low value of one of the bands are corresponding low values of the other bands and the same for the higher value. So you know that from the theory, this is a regularity that has not really a physical explanation, but when the bands are correlated, and all the visible bands are correlated each other, and also the mid-infrared, while all the other bands are not really correlated with the near-infrared band, and this depending mainly from the vegetation. When this correlation exists, this correlation is always positive and is represented by the point clouds that is more or less following the bisector of the diagram. So you see, this is from the theory. There's not really a physical reason of that, but it's a general assumption that you see we can verify. Let's put in the x-axis right now the band 3, okay, and let's put it, okay, And you see that with mid-infrared, there's a sort of correlation, but not so high. And let's put in the y-axis a band of the thermal infrared, 6.1, all right? So we are now mixing reflectivity and emissivity. Let's see what is happening, and you see that this is the classical explanation of the fact that no correlation exists in this case. So, taking into account emissivity and reflectivity, you see there's no correlation at all. And also, if I'm changing band 3 in the x-axis, for example, I put the band 4, the near infrared, you see that again, I don't have any correlation at all. And if I'm put, for example, band 5, that is a mid-infrared, you see again, there's no correlation. So pay attention that here, for the very first time, there's for the first time, you see, apart from this clause that is not correlated, here is a sort of correlation that is a negative correlation. So, because for very low value of band 5, we have a higher value of band 6, for example. Okay, take that, remember that for the next steps. Let's check what we can do with these scatter plots, because this operation allows to make extremely interesting processing. So you see that now here I have class 1 and there's a red. For example, let's change that in green, all right? So we can take part of these point clouds and color that in this class 1. In that color, for example, we can color in green this part of the scatter plots, for example. And in a very interactively, all the cells that are corresponding to this part of the point clouds will be colored in green, for example. How we can do these things here? I'm sorry, I moved that. All right. How we can do that in a very simple way. For example, I want to understand what is represented in this part of the scatter plots. You see that seems to be correlated in a negative way. So let's just left clicking the mouse, keeping press, you are just drawing a polygon, and when you want to close it, release the left button, and you see that in this case, I defined a polygon like in the region of interest operation. Here, you don't need to close that. And in this case, you see that in this part of the scatter plots, I colored in green all the water. You see that is reflecting very low values, very lower reflectance in the mid-infrared, but there's a higher value in the thermal infrared. But you see that with this very simple operation, I represented all the water here. So, for example, if I want to what is corresponding this part of the scatter plots, I'm changing, I'm defining another class. You see, clicking over these icons, I define the class 2 in red, for example. So I'm drawing a polygon here, I'm releasing the left one, and you see that is this particular part of the scatter plots is representing vegetation. So if I'm enlarging that things here, just including all these things, you see is representing all the vegetation in this case. You see that is quite impressive, this interactive operation, because in a very simple way, I can do something that is very similar to the density slice, but using a couple of spectral bands. So working on correlation of the point clouds. Let's do another thing. Let's open our different bands, because I use two bands that are not really significant. So in the x-axis, I visualize the band 3, that is the red, all right? And you see, whenever I'm changing the bands, all the pseudo-color image that I created in colors is disappearing, of course. So in the in the y-axis, I put in the band 4, that is the near infrared. Here it is. So, you see here, let's try to understand in a more ordinate way what we are doing. So, as I said before, the band in the visible, in particular the red in this case, is not correlated with the near infrared band, or rather, it is, in reality, I could observe from how this point cloud is made on the fact that probably there's a series of surfaces that are showing a correlation in this sense, you see, from low value of band of the near infrared of the red, we have variable values of band 4, and there's a positive correlation in which to low value of band 3 corresponds a low value of band 4, that are the near infrared, and to higher value of band 3, we have higher value of band 4. So the question I ask myself is, if I wanted to verify where is in this point cloud the vegetation is, where this vegetation will be in these scatter plots. So let's imagine what we said in the lecture number 5, that you remember we talk about the interaction between the electromagnetic energy and the surfaces on the ground, and especially when we talk about the spectral signature, you know that the vegetation has a peak of absorbability in the red and very high value in the near infrared. So, for example, I'm expect that the vegetation in this part of all these scatter plots, so low value of the red band, and here low value of red band and higher value in the near infrared. So let's see if I'm okay. So not use the red, otherwise we cannot see that. So I'm sorry. Okay, let's use the near infrared. Okay, let's color that in green, because the vegetation is always green for us. So I'm imagining that the vegetation is there, so I'm trying to draw a polygon here. I release the left button, and you see that there's a bunch of vegetation in this part. There are some part of vegetation that is missing, but you see that if I'm enlarging these things here, you see I'm defining all the vegetation. You see, that is very simple to identify. So, if at this point I decided to have a new classes that is represented in blue, for example, because I want to represent the water in blue. We said that the water, as you remember from the theoretical part, in the visible and in the infrared, has a high correlation, and in both cases we have the fact that the water is a good absorber in all bands. So I mean, I'm expecting that the water is along that direction, this direction here, but with very low values. So around here, let's say. So let's try to draw a polygon here, just close to the origin of the diagram, release, and you see that we have all the water. Very easy, you see. So you see, these scatter plots are extremely interesting because they allow us, from statistical data distribution, to understand in a very interesting way, to understand where our surfaces are in the scatter plots, in the point clouds. And you see that using this very trivial operation, I extract a lot of interesting information. For example, here I started all the water and all the vegetation. That is something that is not really despicable things. Indeed, it seems to be very interesting with a very simple operation. So just drawing these clusters that is done only in qualitative way, of course not in quantitative way, is extremely interesting because I mean the scatter plot is helping us, especially in the phase of exploration of the image, to understand if any correlation exists, and if this correlation can be used in order to build from this image a false color image, colored image, in order to extract this information and associate it to the different color information. So you see here that in reality, this operation that I'm doing from a qualitative point of view can have a sort of relation to the quantitative way. So starting from this consideration, you see here, we can do the same things here using what we learned in the previous lab. So we can go to the band math here. So you see I'm opening the band math, and so I'm defining an interval in the red, for example, in the red band, in this red area, for example, in the red band comprised between 0 and 80, for example, in the near infrared from 0 and 40, in order to extract all the water. How we can write this expression? Let's look. I'm open the bracket, B3, that I will associate to the red band, GT greater than 0, close the bracket, space, and open the bracket, B3 space less than more or less 80, and I close everything. So in this case, I'm extracted all the digital numbers in the band 3, in the red band, that are comprised between 0 and 80. Very understandable, right? But I want also to connect, to intersect all the values that are in the near infrared in band 4 from 0 and 40. So all these things should be related to a second condition. So I need I need to add another end and this other condition, that is open bracket before GT 0 greater than 0, space, and space again, open the bracket before space less than LT 40, for example, and close the bracket. All right? So you see, I intersect two different conditions that is related, that is connected by an and I will extract all the values that are represented in this red polygon I have here. So press enter in the band expression, there are no errors. For example, if I'm adding another bracket, you see, just press enter, I have more brackets, so let's erase that. Okay, press enter, there's no problem. So now I can press OK. I am associating to the band 3, to the B3, the band 3, and to B4, to the variable band 4. All right? Let's put that in the full scene. They put that in memory. Let's use a file. So let's choose the name. For example, let's call that, for example, I don't know, XXX. All right. I already have a file like that, but okay, I can save that. And you see, the data has been processed. All right. So you see, you remember that I mean it's completely black, but it's depending from the auto stretch that is the default option in MV. All right. So we have also, in this case, we have also a black and white image. So right-clicking on the layer manager on the XXX image that I actually created, you see I'm got a new raster color slice here using this particular processed image. You see I have only two bands. You see I can change the color. The class 0 is not interesting because I could represent that in black, while 1 that is water, I change that in blue. All right, you see here that the results is very similar to what we were expected because we extracted all the water. So you see, let's extract now, try to extract the vegetation. All right, let's go again to the band math. Let's use the previous expression, but we are changing now the ranges. In B3, the ranges are ranging between 0 and 80, more or less, you see, in the band 3, while in band 4, in the near infrared, they are higher. So they are ranging from 70, more or less, so greater than, instead of 0, 70, to 150 in this case. We're substituting 40 to 150, all right? Press enter, and let's check if we have the expression is correct. Of course, these two examples, they are not, they are two sets that are not intersecated. Okay, let's press enter if checking if the syntax is correct. All right. Okay, so for example, if I'm adding another brackets, I have an error. Okay, press enter. This is correct. Let's okay. I am associating B3 to the band 3 and associating band B4 to band 4. Here it is. I'm saving that in, for example, XXX1. All right, I'm opening and pressing OK. Now all the data is processed. All right. Again, we have a very black image. All these images are represented by 0 and 1 values. So right click on the XX1, new raster color slice. Okay. Now 0 value is something that is not, I'm not interested in. So I'm changing the purple and for example here, let's change that right click in black, while what is interesting is the value 1 and then changing that in green. All right, so you see, okay, you see that I have all the vegetation in this image. You see, so in this case I have all the vegetation, and in the other one I have all the water. So for example, if I'm taking out the visibility of that, I'm sorry, I will also to take that out, the visibility of okay, of, I'm sorry, yeah, let's put the top, okay, all right, let's give out the visibility, all right, you see here in blue I have all the water, all right, and in this case, I have the extraction of the vegetation, you see, that are complementary to each other, you see, they are not, I mean, there are no cells that have both the classification. There are no cells that are all water and vegetation in the same time. So you see how these scatter plots are important. So let's imagine at this time to perform a lot of operation using the scatter plots. So let's try to exercise by yourself in this way, using, for example, other bands, and trying to extract from these images, try to extract in color with the scatter plots in color different surfaces that you have. For example, let's do that in the scatter plots and then try to open the band math and to redo the operation like in this case. Because I mean, this is only an example that we perform using the scatter plots. All right? So let's close these scatter plots. And now we are beginning the second part that I'm terminating this part. To close all these files because we are not using these files. So in order to close everything, I'm going to the main menu, you see here, file, and I'm going to close all files. What does it mean? I'm clicking here, yes. What does it mean, close all files? Close all files means to close all the what I have in the layer manager, but you see that also in the third manager, I don't have even anything. So I mean, everything has disappeared from the possibility to display. So in order to start the second part, in the data duet available, out of the different folders in the data one, there's a particular file. So let's go into open as a generic file. You see here, just clicking open. I'm going to the data. You see here, the folder. All right. And you see that here, outside of the folder, there's the Kodak grayscale. You see? I'm opening these things here. All right. You see, this is the file. I'm zooming out that in order to see all the different images. So I'm pan and I'm centering this Kodak grayscale. What this Kodak grayscale is and why we are using that. So this Kodak grayscale is what is generically is called radiometric wedge. That you see that is very old. It's 1977. That radiometric wedge was used usually to calibrate the radiometric component of the printing of the photographs that we are used to call panchromatic. That is something that generally the terms is used black and white, but I mean that was for understanding the quality of the printing product of analytical photograph. So this radiometric wedge was used usually in order to understand how my acquisition and output system was able to represent the fidelity of the different gray tones. So these gray tones are nothing more than these 20 different bars, you see, starting from the letter A till to the number 19. So there are 20 gray bars starting from the number A, that is the white one, and then 19, that is the black. All right, which is the characteristics of this radiometric wedge, in which, of course, we are interested in the bars part, of course. The characteristics of these bars are that they are at constant intensity. So when you are passing from one bar to another, you see from A to 1, there's a decreasing of the gray tones, the intensity, that is the same that we have from 1 to 2, 2 to 3, and to every single neighboring bars. So in order to understand what is this decreasing, if we have 20 bars, and if this radiometric wedge had been acquired with a radiometric resolution of 8 bits, that means that we have 256 different radiometric values. So if I'm dividing 256 by 20, from one bar to the closed one, we have more or less 25 different intervals divided by 2. So that means that we have 20 bars. It's more or less 12 different digital values of difference between two neighboring bars. So that means that if the bar number 1 is 255, because it's the maximum, the bar number 1 should be 255 minus 12. That means that that could be more or less 242 or 43, something like this. And all the same for the other bars. So fundamentally, these bars are characterized by the fact that they are equidistant from the radiometric point of view. So in this case, this radiometric wedge, that is something that is printed on a photographic card, that I mean is covered because I mean should not be used too many times, because otherwise with the light could be, of course, decrease the quality. So usually this radiometric wedge was acquired by a digital camera, an analogical camera in that way, was printed, this film, and then was compared the two wedge, the results of the film printed was compared with the original radiometric wedge in order to understand the quality. In this case, transferring in a digital form,
I use this radiometric wedge. This is printed, and I acquired that with a scanner, with a flatbed scanner in one lab that we have at the Polytechnic. And I mean, this particular scanner that I use in order to acquire these things is a professional one. It's a photogrammetric scanner that is acquiring with a very high geometric resolution and is really working like a multispectral camera that we have on board of satellites, because we have one arm that is moving across in the scanner across the width of the plane that we want to acquire, and on this bar that is shifting, there are all the CCD detectors that are acquiring what is reflected by the bar. This is an opaque support being illuminated by the white light that we have inside this photogrammetric scanner. And so this CCD scanner you are acquired in a push broom mode, and you will see that in the theoretical part. So I mean, this scanner that we have in my office is working really similar to a push broom scanner mounted on board of a satellite. So we are using this synthetic image because, of course, it's not acquiring something on the ground, but in order to understand using this particular wedge, that is, of course, a calibrated sample, a radiometric wedge, how to simulate what is acquired by the real multispectral scanner mounted on board the satellite. And you remember that in the theoretical part, I also mentioned that this kind of radiometric samples are also used in the pre-calibration phase of the sensor once he is mounted on board of the satellite and the satellite is already orbiting, in order to understand the quality and to check the quality of the scanner mounted on board of the satellite. You remember that we have something that is very similar to that. I mean, having on the ground, on the Earth's surface, of course, they are very big, and they are acquired by the scanner on board of the satellite in order to check the quality. So in this case, we are using these things in order to understand, to fully understand how a multispectral scanner is working, because I use a very similar one, and which are the characteristics of these scanners. So this radiometric wedge you see here, I move that here, all right, because now we are using another command, a new command that we have not ever seen before, that is in the main menu here, in the display menu. So, and again here from 2D scatter plot, now we are using the profiles, and in particular we are using the horizontal profile. You see, we have this window, you see, and now there's an empty window, because you see that the cursor is changing in a cross, in a red cross, you see, in the display. So I'm taking the select here as icons. I move these cross and I put that over the bars. So I'm proceeding with an horizontal profile. So I mean, you see, I'm trying to put that in order to have the same reference. Okay, you see here, it's more or less the same. All right. What is a radiometric profile? The radiometric profile is a diagram in which in the X file, you see here, you have the column. So I mean, the different cells that are represented. So in this case, I mean, we have the column of the images, all right, from 0 to around 100 and 1500, that is more or less the width of the image. In the y-axis, we have the digital values, you see, ranging from 0 to 255. So, I mean, if I put that, for example, here in the grayish part, you see that is a particular profile. Here, you see, it's a very classic, very typical. You see, it's a sort of scale, you see. In the first step of this scale, you see here, is characterized by, you see, you have every single step. of this particular scale. And see here, because this is a sort of section, a transit from the radiometric point of view. So in this case, you see, I'm just observing here in the bar A, I'm reading the values here in lower left part. You see that the values is 255. So it's saturated. You see here? And this is the values of this bar number 8. So if I'm going here to the border of the bars number A and 1, you see that after the border, the radiometric border, you see is 244. You see? When I'm going to the first and second bars, we are passing to 237, then 212, 163, 143, 131, and so on. You see? This radiometric wedge is allowing us to have this radiometric profile in order to fully understand what is happening in the acquisition phase. Because you see, we can use that as a stair, like our home stair. And if we are using that as a stair, I mean, all the horizontal part of this stair that we are using that should be absolutely horizontal, while all the vertical part of this stair should be really vertical. All the horizontal part of every single step should have the same width, and all the vertical part should be of the equal height. So, but you see, beside the fact that I use a scanner that is costing tens of thousands of euros, you see here, the horizontal part of every single step of this particular step that we are representing in the horizontal profile, you see, but when we are going to the very dark bars, you see here that is not horizontal, this part. So that means, you see, why? Because, I mean, in that particular bars that are very dark, I mean, the signal is fluctuating. And when we are also going to this particular bars very dark, I mean, the different steps are not really distinguishable. And you see here, there's also a problem here. But starting from this bar, and you see, the noise that we have in the horizontal part that should be homogeneous from the radiometric view are not really is not really homogeneous, and you see that I cannot really understand if there are steps. So I don't understand, and we don't see in the values. In these values 11, I have 72. In the second, in the 12, I have 67. In the 13, I have 55. Here 49, 42, only 6 or 7 different values of difference instead of having 12 as before. So you see, it's flattening with darker values the digital number. So you see here, this means fundamental that I mean that is a physical evidence that if you see here the stairs, it's quite accurate, or more or less accurate when we have very high digital numbers. So that means that when the radiance that is coming from the ground is quite high, that means that the sensor is able to, I mean, accurate, describe and convert these radians into digital numbers. While when we have a very low radiance that is coming from the ground, that means all the darker bars, the scanner is not able to understand and to represent the radians separated in the different bars. So that means that you see, for very high value of radiance, the sensor on board of the satellite is able to discriminate better than darker values from the statistical point of view, that means that with higher variance, other radiance coming from the ground, we have higher variance of the data, so higher standard deviation. When we have in lower value, in the darker bar, you see that, the standard deviation of the variance from the statistical point of view is very low because all the data are converging around the mean value of all these different bars, for example. You see, all the values are comprising a very small range of digital numbers. So you see here, if I'm zooming in, so you see these different bars here. I'm sorry, I need to use the pan. When we are going to the darker values, you see, it's difficult also just by watching that to understand the difference of the different values. So you see, in the reality, it's working really like our eyes, because when we have lower radiance that is coming to our receptors in our eyes, you see our eyes is not really able to understand the difference because they are not so sensitive. Why? When I move into a bright value, you see that to our eyes, it seems very clear the difference between the different bars, you see. So you see here that, as we said before, these bars, the steps of this stair is not really horizontal. So that means that you see here, also for these values here, this one here, where I have the cross, the red cross, I see it is not flat. So there's the digital number that is fluctuating. So that means that, this bar should have the same values and the same digital number. But you see that it's ranging in a very small range of values, but it's ranging. So it's not flat, it's not horizontal. So there's a sort of entropy in which is the signal, the radiance is recorded on board of the sensor. I'm sorry, I'm zooming out in order to move to the other values, and you see that this noise, these fluctuating values, because this noise from the signal point of view, you see that when we are going to the darker bars, this this noise is higher than the bright bars. That means that having low radiance coming from the ground, I also have more noise. But I have another problem, another issue that is what is not really clear here, but if you check it, but in these things here, I'm closing it here, and I'm do that again. So I'm going to redisplay the profile, the horizontal profile. You see, I'm moving the red cross here. I'm good. Let's select that. Okay. Here, you see why the radiometric profiles of the first bar is completely horizontal. There's another problem. So in the radiometric border, you see here that are representing more or less the different steps of the stairs. You see, are not perpendicular. You see, but they are inclined. What does it mean that are inclined? This is not really easy to explain, but it's very important. I will also explain if it's not clear. I can explain that in one of the question and answer session that we have during our slots. So when we are acquiring an image, you have to imagine that the result is a matrix, right? Like a net, where every single piece of this net is representing a cell of the image. And the dimension of this particular piece of the net is the same of the geometric resolution. So let's imagine that when we are acquiring, this is a paradox, of course, the acquisition mechanisms is something that when I'm launching a net, all right? So I'm launching a net with every single piece of the net that is equal to the geometric resolution that I have on the ground. And when I'm launching this net, this net will be on the ground, and the origin of this red, of course, will be random, in a random position. So every single piece of the net, every single small square on the ground will be placed in a random position. So that means that in every single cell of the cell, I'm proceeding from the radius point of view with a random sampling, and when I'm acquiring the radius that is coming from the surface that is comprised in a single piece of the net, in every single cell, I can have different surfaces that are reflecting the electromagnetic energy. And so on the sensor, on the CCD detector, I will take something that is the average value of the different surfaces that are reflecting this particular spectral bands. So when I'm acquiring this radiometric wedge, of course, the random position could cause the facts that I mean a cell of the image matrix of this Kodak grayscale is in the middle of a radiometric border. So it's staying and is representing two different bars because it's in particular in correspondence with the border of two bars. So if I have there a cell that is taking one value, you see here, for example, in this case here, you see what is recording, just consider this square like a cell. So part of the radius that is registered is coming from the bar number 1 and the other from the bar number 2. How will be this radiance? Which is this radiance? This will be a mean value that is calculated over the area of the two bars, but of course, the radiometric values that is converted by this radiance that is coming on the detector is something that will be in a sort of mean value between the 1 and the bar number 2. And so that means that this is explaining why the vertical pieces here are not perpendicular, but they are inclined, because by the sampling of the image matrix, I mean, in this case, when you have these vertical pieces of the stair, that is of the single step that is inclined, that means that the cell of the sampling is between two different bars. In this case, I want just also to highlight another things in order to finish the introductory part. This radiometric profiles in this synthetic image is used in order to make you understand the things that when we are talking about digital filtering. So these digital filters are operations that are trying to extract from this image two different components that is very important and very unbelievable in the results. That means that in every single image, and you know that from the theoretical part, from satellite images or whatever image, I mean, in every single image, there are two different components, all right? And this is very, very important. So that means that I have low frequency and high frequency every single image, and I can see from this profile. So, for example, the low frequencies are the horizontal part of these radiometric profiles, where I have a very low contrast, you know? So all the horizontal part of this different step of this stair is characterized by having a very low frequency, all right? While when I have the vertical pieces of this stair that is connecting the different steps, there I have the high frequency component, where in two adjacent cells, I have two very different radiometric values. So I have a radiometric border. So you see, for example, if I'm putting that in the text, you see, I mean, I have a grayish background, and the letters that are white, you see, they are very high frequency values. You see, Then in correspondence here of these circles here, you see I have also high frequency, while in the background, you see I have something. If I'm going to the black numbers, you see I have a high frequency that are changing from black, very black, to a gray tones of the background. So you see, dark letters in a grayish background have very low values, while the background has a higher values. So these are high frequency values. So in the bars, the horizontal part is the low frequency component of the image. The vertical parts are the high frequency part of the image. So let's now see how to implement the digital filtering. So I mean, the horizontal profile, I think that we have said whatever we need, so I can close it. All right. And I move that in the center of the display. All right. And now we are talking about the digital filter. So the digital filtering are in the toolbox, because it's not things that we are doing in visualization. So you see that when we are going here, we have here the folder filter. You see here there are many different filters here, but we highlight our attention in this part here, in the convolution and morphology operation. So if I double click here, you see I have this window. All right, and from today we will start to open this filter. So you see here we have a high pass filter, but I want to start with the low pass. So in order to select a low pass, I'm going to the button convolution and I'm selecting the low pass. You see here. You know from the theoretical part what is a kernel, right? So I'm not going to describe the submatrix that is used for the convolution, the operation. You have all the reference in the theoretical part. And so in this case, in the low pass, the kernel size is fixed to be a square. So I mean the number of rows is equal to the number of lines of the kernel, and all the operation that we are doing is applied to the barycenter of this kernel. That's why I mean that should be odd number of column and rows. All right. So I mean, for example, here the low pass is simply, as you know from the theoretical part, the calculation of the mean value or the median value or something like that. So I don't want to reply whatever I already explained in the theoretical part, but I want to implement these things here. And this low pass, of course, is extracting the low frequency of the image. So in this case, let's go and let's try to enhance the low contrast part of the image, where the low frequency are the parts of a very low contrast. So in this case, they are the bars, the inner part of these bars. So with this low pass, we are trying to extract the low pass, the low frequency. While with the high pass, we will extract the high frequency. That means all the radiometric borders of these different bars. All right. So let's start with the low pass. You see, let's use a three kernel of the dimension of 3. Let's open. We are using the only file that we have opened. Let's open that to the spatial subset of the full scene. You see here is more or less 1050 by 500. Click OK. Let's put that in memory. All right. And this is OK. OK, you see, this is the results. And this is already in the layer manager, top of the list. All right. So I mean, for all this operation, I mean, there are many calculations, but you see that it is almost in real time. So how many times these kernels pass from these things here? Let's see. You see, it's 1500 by 500, more or less. So it's passed all these times. 1500s times 500s, more or less. We have this kernel passed. So I mean, it's very quick in the implementation in MB. You see, if in this case I'm just zooming it, the results, this is the memory 2. In this case, you will have the memory 1. This is the original image, so I gave out the visibility. You see, I see very well the different bar, the difference between the bars number 1 and 2, for example. When I'm visualizing that, you see that the bus number A1 and 2, there's no difference. And when I'm going to the very dark, you see there are no difference at all. I mean, so that means that I'm lowering the contrast of the image. So also the written part, the contact grayscale, you see that when I'm taking the low pass image, you see is the focus. So the typical effects of the low pass filtering is the focus effect. So let's recall the convolution and morphology. Let's apply another low pass, and I'm applying that to the already filtered image, right? So I mean, I'm implementing another filter. So I'm filtering an already filtered image. I put that in memory, and I'm doing that. You see, this is the result. So see if I'm going here, you see, this is the original image, and then when I'm putting the filters, filtering and filtering again, you see that is I'm lowering the contrast, and so at the end I will have something that is really the focus. So let's do the last operation again. Let's imagine to use a very high kernel. Don't ask me why I'm doing that. You will understand that in another part of the image of the lab. I mean, enlarging this kernel means to proceed with many filtering operation. So using, for example, this 35 kernel size is just to think to have the low pass filters applied 10 times using a kernel size of 3, for example. Let's imagine that. Let's apply that to the original image. All right, I'm starting from the beginning. I put that in memory. So in my case, it's memory 4. And you see, this is the results. You see, that is simulating these things here. What is happening after many different low pass filtering? You see the image is completely defocused. I cannot read even the written part. And you see the bars are completely not clear. So if I'm proceeding with an infinite number of filtering, okay, let's select the original image. I gave out all the visibility. This is the original image. You see, right-clicking. Let's see the quick starts. All right. So in the quick starts, of course, I have only one single band, and there was also all the other. The mean value of all these radiometric wedge is more or less the mean value of 0 and 255, more or less, you see? All right? So the mean value is the distribution of 256 values. If I'm filtering in low pass in an infinite number of filtering, the results at the end, I'm lowering for every single operation, and this is the histogram you see here. Don't take into consideration all these different peaks because these are the peaks of the bars. So if you are considering this part that is the original histogram, if for every single low pass filtering, I'm closing the dimension of this value. You see here, because this is representing the contrast. Because I mean, the maximum value more or less is the mean value. So every time that I proceed with a low pass filtering, I'm closing the value of the distribution because all the values are converging to the mean value. So if I'm filtering low pass for an infinite number of times this is the original image, at the end, the image, the resulting image will be an image with one single value that will be the mean value. This one, 129. So having every time a mean value, at the end, all the values will be the mean value of the original distribution. You see? So I mean, at the end, this is a very particular histogram, because I mean there are the bars. But if we have only this second part, at the end, all the values, I mean the values will be represented by a single vertical lines. This one, you see, pointed in 129, more or less. You see? Okay, all the values will be pointed in the same digital values. Of course, you will see these things here. You see here, okay, this is a sort of test to simulate many different digital values. I'm doing another things, 35, but I'm applying that to the last image filtered. So put that in memory. All right, and you see that filtering, we can do another one, maybe enlarging also these things here. So for example, I'm going to, I don't know if I can try just digiting with my keyboard. I think that the maximum is 65. You cannot do. Okay, I'm the last one. I'm filtering with a kernel 65, and you see that at the end, of course, we are converging to the values. You see that is changing from white to black. At the end, we will have in the bars the mean value that will be the values to the bars that is in the center of the distribution. All right, so we extracted with the low pass the low frequency. All right, so let's give out all the visibility, because now, and I'm centering that, zooming out and panning that. All right, now I want to perform an high pass value. So I'm going to the convolutional morphology. I take back the kernel size in something that is acceptable, that is 3, for example. All right. In convolution here, I'm selecting, you see here, high pass. In this case, the high pass is extracting the high frequency. This is the kernel. In this case, you can modify the kernel. So you remember how the high pass is working. That is something that is, I mean, all in this kernel, all the adjacent cell to the correspondence to the Barry center. I have a mean value of all the adjacent cells, and the mean value of these things here, of these 8 cells, is subtracted to the original values in the center position. So if the values is similar to 0, the difference, that means that these pieces of the image is at low contrast. If this image is different from 0 in negative or positive value, that means that this very small zone is characterized by a high contrast. All right? So that means that the barycentric cell has a different digital number in correspondence with the neighborhood cell. So all the high frequency value will be highlighted, and in the high pass, whatever is a low frequency will have as a result a value very similar to 0. All right. So all the adjacent radiometric cells are multiplied by -1, so we'll read all the digital number in a negative value. We sum all these 8 digital number in a negative. I multiply by 8 the central value, and I sum the central value multiplied by 8 and all the other values with the negative values. If the value the results is equal to 0, there are no contrast, so there's a low, I'm sorry, a low contrast, the low frequency component. So let's apply to the original file that things here. Let's tell OK and put that in memory. All right. And in my case, it will be the memory 7. All right, this is the results. You see, that is very strange. And it's quite unbelievable because you see, whatever is low contrasted is very homogeneous. So you see that all the values have more or less the same gray values. So all the low frequency have been deleted, while what is have been extracted is the borders of the single bars. So you see, if I'm going to check my radiometric profile here, the horizontal one, and I'm taking the cursor here, and I put in that, you see here, that the profile is very horizontal, and the fluctuation, you see here, that one, is the border from the different bars, you see, here. So I mean, the high pass is very impressive, and this thing is very clear when you are going to the text or to the number. You see that characters here have been extracted in a very nice way. You see also the numbers, and you know that all the OCR software that are recognizing the characters are mainly using high pass filtering, because from all these images are extracting these borders of the letters that are interpreted like the real character. So for example, if I want to use the K value, I mean, I have the border, I have the software that is high passing the image, is extracting the border of K. The border of K is very similar to K, is interpreted as the character K. All right. So converting that in the K character that you can read, for example, in your word processor, for example. So the OCR are working using high pass. So, but what I want just to show you is something that is really unbelievable also from me when I saw that the first time many years ago, and it's very impressive that things here. So I mentioned the fact that the high pass and low pass filters are dual. So if I'm performing a low pass, and if I'm subtracting from the original image the low pass component, I will have the high pass component. So in another way, if I'm subtracting from the original image the low frequency part, the results will be the high frequency part, and of course vice versa. So if I'm subtracting from the original image the higher frequency, the results will be the lower frequency. If I'm sum low and high frequency, I will have the original image. So this is really impressive, these things, but let's try to implement it. All right, this is the high pass filter, okay, the results of the high pass filter. And I extracted all the radiometric borders, all right? So whatever is in low frequency is converted in a very similar gray tone. How we can do these things here? I gave out the visibility. This is the original image, you see? We can simulate that with the band math. So I'm going to the band algebra. I'm using the band math. In the band math, you see, it's very simply the expression I'm using. So I'm using the variable b1, for example, and I'm subtracting the variable b2, b1 minus b2, right? So if I'm taking the 2b2, the memory 2, and b1, the original image, the results I'm expecting to have something that I have in my case in memory 7, so the high pass image. So I need to press enter in order to I'm sorry, redo that, I'm sorry. So from the original image, I'm subtracting this one, the first low pass, the results should be this one, all right? So let's try, let's go to the band math. I'm just write down B1 minus B2, all right, enter in order to check if there's no error, of course. I'm associating to B1 the original image, the Kodak grayscale, this one, all right? And to B2 variable, I'm associating what I have in memory 2 in my case, the first low pass filter convolution of the original, all right? Put that the results in memory, and in my case it will be memory 8, more or less, all right, okay. Okay, so in this case, I'm pressing OK, all right. And so from the original image, I'm subtracting the low pass filter, and the results should be the high pass, all right? That's really unbelievable, you see? This is the result. This is the memory 8. This is the 7, you see? 7, 8, 7, 8, 7, 8. That's impressive, you know? Because that is definitely make us understand that all the image are composed by low and high frequency. And when they told me the first time when I was really young, I was thinking that they were pulling my leg, because I mean it's very unbelievable that things here. But I mean, I can do also the dual operation of this one. I can subtract the high pass from the original, having the low pass, but I'm not doing that that things. But I mean, this dual property is also true for the our satellite image. So let's open another image. Let's open recent because, for example, I already used the north east southeast part of the America. So you see, I'm reopening the image of the United States. All right. So now I see everything mixed. So the Kodak grayscale is not geo-referenced. So it's better to close everything here, because otherwise, I mean, this is the image of the southeast of the states that I open as a recent file, because I already used that in the first part. So this is the visible part. Why we cannot try to use not a low pass, because it's not really useful for us, but we are using the high pass. And for example, we are using only this part. I'm zooming the Cape Canaveral part. You see there are roads, there are buildings, there are water, and so on. We are going to the filters. You see here, convolution and morphology. I'm using a high pass 3x3. And as usual, here I have the 3 different data sets. Okay, you see here. So the first one here is composed by 6 bands. So this is the bands that we are actually visualizing, 3 of that. The true color, the bands that we acquire in the visible part of the spectrum, of course. And this operation, this filtering should be done here in spectral subset. We can decide to how many bands filter, but in the spatial subset, we are not filtering everything. So spatial subset, you see, I'm going to the button image. You see here that when I'm selecting with this border here, this corner of the frame, red frame, for example, I'm forcing that 3000 by 3000, for example, I'm putting that more or less in the same area that we are looking at in this moment, all right? And then clicking OK. All right. And I'm filtering the high pass for all the 6 bands in all this, all in this part. Let's put that in memory again. Okay, I'm forcing that, of course, as usual, I'm forcing that in memory, and I click OK. You see that is very, very quick. All right. And this is the result. You see, the results it's again here very strange and quite impressive. If you are taking the original, you see here, and we have the high pass filters of the original image, you see that these high pass results is very similar to something that you all know. You see all the low frequency are the same gray tones, and the high frequency are all very bright or very dark. All right. So you see these are the convolution of the three visible bands in this case. All right. So these images remind you something, but of course, it's remembering something that is very similar to a map. You see that with the iPass, I have all the roads, I have the border of the channels. You see here, I have the polygons of the buildings and whatever. Because if you are thinking about maps, I mean reference maps, these reference maps are not something different than the representation of radiometric borders. For example, hydrography, I mean the border of the rivers, and for example of the coastline, is represented simply because, for example, a river, in order to be seen by our eyes, should be different from the neighboring area. And so when you can understand from an image, simply staring at this image, that I mean, this is a river, just because, there's a shape. And if you are performing a high-pass filter, you are extracting radiometric borders. In maps, you see, whatever we are representing, apart from the altimetric layer, that is a representation, it's a matter of radiometric borders. So, for example, in the middle of the sea, there's nothing to represent apart from ships, for example. But of course, being so homogeneous, you cannot recognize everything. If you are in the middle of the desert, of course, you have nothing to represent because everything have a very low contrast because the sense is reflecting in the same way. So in mapping, whatever we are representing is radiometric borders. And the only things that in mapping is not representing like a radiometric border is the high component. Because, for example, the highlight, the lines that are representing the different point at the same heights are interpretation of a digital elevation model, and is not something that is apparent on the image. So, for example, in this case, if we are taking, as before, we are taking from the original image, we are for every single band, and we are subtracting the high pass image, the results will be the low pass. But I want to show you another things. So in order to make you understand that these low and high components are present in every single image, let's go, for example, in internet, all right? So I'm opening a new tab, for example. I'm a fan apart from the Juventus football team, but I don't want to bore with you. I'm a fan of American football, and I'm a very a fan of this football team that is the New Orleans Saints, because I've been there for a while in New Orleans. And so you see, this is the logo. Okay, that is. You can imagine that this spot is quite stupid for the Italians, but I really love that. So, for example, I can take an image out of here, whatever image, for example, you see? This is a very low image because we lost this game against the Green Bay. Let's take this one that is big enough, that is more or less 2,500 by 1,700. Okay, I'm saving that, you see. I'm okay, right clicking, and I'm saving this image with the name. All right, I put that like I don't know. I know these two players, but let's call that Saints. This is Drew Brees that was retired, and this is Michael Thomas, the wide receiver. All right, all right. Let's go to the download in order to take. You see, I mean, it's very small. You see, it's not 2000 by 2000. Okay, but let's open that. All right. Let's close everything here. So we can free the memory, the RAM memory. So I'm going to the main menu file. All right, and let's close all files. All right. Okay, so I'm closing and I'm free all the memory. Let's open the image. You see, I'm opening in order also to make you understand that Envy is able to open whatever image you have. So I'm going to download. Okay, Saints, let's open that. All right, you see here the image. I mean, it's not 2000 by 1000 and a half because in the data manager, you see, in the data manager, what is very strange, it is, I mean, it's a color image, but in Envy, I mean, Envy split the three different bands. So this is quite important. So the color image that we have in Envy are used, I mean, Envy is interpreted like three bands indivisible. Blue is band one, three is the red, and two is the green, of course. So this is the first thing. File information, you see, that is, I mean, is 300 by 225, but we don't care about that. You see that is in bit. So this image is band interleaved by pixel, you know? So this is a case in which this is not a BSQ, this is not a band sequential. This is bit. I don't know why it's bit. And this is JPEG, all right, the format. All right, so very good. So these are two very famous players. This is Drew Brees that was retired this year after 20 years. And this is Michael Thomas, that is a wide receiver that is earning many millions a year. All right. In this image, I want to extract the low frequency. So let's go to the convolution and morphology. All right, here. I'm selecting the low pass from convolution. All right. And I'm applying that to the only image that we have. Press OK. Let's put that in memory, of course. And this is the results. And you see that the results, you see, is that in this image is very much apparent than before. You see, this is the low pass, and this is the original. You see, that is the focus. I'm lowering the contrast. You see, the number, the visage of Michael Thomas on the helmet and whatever, also on the symbol that they have in the helmet. You see, this is very Italian because it's coming from Florence. You see, that is completely the focus. You see, in the low pass, I mean, I cannot distinguish the symbol of the saints. All right, so let's do the band math. So I'm taking B1, recalling B1 minus B2. So if I'm subtracting the low frequency from the original, so B1 I'm associating, so remember that we have three bands. So I cannot do to all the color image, I'm using one of the three bands. So to the B1, I'm associating the band one of the my memory 10, that is the original image, what I call the saints, all right? And to the B2 variable, I'm associating the low pass filtering of the same band, this one, all right? Okay? So let's put that in memory. Let's press OK, right? You see, this is very unbelievable. You see here that the result is the high pass filtering, in which in this case we are starting all the radiometric volta. So we have the contour of the helmets, of the arms, of the body, of the numbers. And you see, this is the original image. You see that in the original image we have something here, and you see I have some people there, and you see I have also here the border of the jersey and of the arm, and I have all the different details of of the things here, you see, that is not really flat, this part of the jersey. And you see that is more clear, these things here, you see? And, you know, it's not very elastic, this material that have been used for the jersey. But it's really unbelievable, these things, because this is the final proof that, I mean, whatever image is characterized by low component here and high component, this one. I'm trying to do the last things, but that will not be working, but I'm trying. Band math, I'm using B1 plus B2, right, as could be not working, but for numerical problem. So now I want to add from the low pass and high pass in order to have something that is similar to the original image. All right, that will not be the results that we are expecting. So I'm associating to B1 the high pass filter, the results of the band math by B1 minus B2, and to B2 I'm associating the low pass image. I put that in memory, and you see, that's unbelievable. You see that the results is, of course, the panchromatic part, but you see, this is really impressive in my opinion, because you see that whatever image, this one, high and low, the results is that one and the original image. This is really unbelievable. So, I mean, always unbelievable every year. So we can finish this lab number 7. I thank you for the attention and take care and never give up. Bye-bye.